How about let's roll a wheel or a ball. What should it be? How about a ball? Make it a which one is in the book here? Make it a solid ball. How about a hollow? We'll make it like a true, most balls, basketball, something like that, is a hollow sphere, right? So we'll make it a hollow ball. We're going to release it from rest. It starts at some height h. And we want to know how fast is it going when it gets down here. How fast is it moving in this direction? Right. So it's going to be rolling also. Now our surfaces have to have friction for there to be rolling. Otherwise it won't roll, right? It'll just slide down the incline. If it rolls, it's because there's some friction there. But we don't concern ourselves with any energy loss from that friction, because what we say is that our objects are all very rigid and they don't deform at all, and so we don't have any energy lost in this case. When things roll, you do get what they call rolling friction, which is what happens when there's some deformation. So let me give you a quick example here, sort of on the side. So let's say you're driving your car down the road, and what happens to your wheel? It's not perfectly round when it's rolling, because it bunches up. The rubber's soft, right? And it bunches up a little bit as it rolls. So if it's rolling this way, it's going to bunch up a little bit in front here. Right? As it rolls, the rubber deforms a little bit, forms a little bump right there. That's its deformation. Of the wheel, right? The rubber gives a little bit, deforms, and so that causes you to lose energy. If you started this wheel rolling and there's rolling friction like that, there's some deformation, the rubber bunches up a little bit, and the wheel has to sort of get over that, and the rubber bunching up and stretching and bunching up takes energy. It heats up a little bit, right? The wheel would eventually come to rest. If the wheel was perfectly rigid and the road was perfectly rigid, there's still friction between the two surfaces. You start it rolling, the way we view it is, it would roll forever without slowing down. There's no loss there. We're not going to concern ourselves with rolling friction. This is why they say if your tires aren't properly inflated on your car, you don't get as good gas mileage. If you properly inflate the tires, they don't give as much, right? You get them properly inflated. When they're not as full of air pressure, they deform more, you get more rolling friction. And some tires are designed to have less. Nowadays you see a lot of choices. You'll see they say low rolling friction tires, you get better gas mileage. Okay, so that's rolling friction. We won't we won't deal with that. So as far as we're concerned, there has to be some friction on that surface for the wheel to roll, or the ball, or whatever it is. Otherwise, it's not going to roll. It'll just slide with no friction. But we don't lose any energy to that. Okay? So this is an energy problem, right? We've got it starting out at some height. It comes down. It's moving. It's an energy problem. We're going to say our initial energy is going to equal our final energy, because we have no losses due to non-conservative forces, to friction. And we have no external forces coming into our system, because we're going to define our system to include the Earth. And so what do we have? Initially, we could have kinetic energy. We could have gravitational potential energy. We could have a spring, but there's no spring in the system, right? And at the end, we could have, we could have, there's another type of energy now, right? It could be rotating. And at the end, it could be translating. Oops, that's an F. Could be translating, could be rotating. And there could be some gravitational energy at the end, right? No springs in our system. So, what did I do? So, at the beginning, is it moving? No. Is it rotating? No. But it is above the lowest point. So we'll call the lowest point 0, which means at the end, we've got no gravitational energy. So this is our energy equation. We start out with gravitational energy. We end up with the moving plus rotating. Okay, so this is a little simpler, I think, because really what's happening, it's not moving and rotating, it's rolling. But we're going to say that's identical to, and I could show you in a little bit later, it's identical to it pure translation plus pure rotation. Okay? So now we can put in, now we want to combine, we want to try to combine these two terms on the right. So there's a relationship between omega and v when something is rotating, right? We talked about that yesterday. V equals r omega, right? The velocity of the center mass for rolling motion. The velocity of the center of mass is r omega. So we can substitute in here omega then, that is v center of mass over r. And then the only other thing we're missing is the rotational inertia, I. How do we get that? We look it up in the book here. In our book, they list a bunch of different objects, disks, hoops, rods, and spheres. They've got solid sphere, they've got a hollow sphere. So a hollow sphere rotating about its center point, the rotational inertia is 2/3 the mass of the sphere times the radius squared. So I, for this case, 2/3 the total mass times r squared. So let's make those substitutions. We've got an mgh here. We've got a 1/2 m, the velocity of the center of mass squared. We've got a 1/2 I. I is 2/3 m r squared. And we've got an omega squared, which is going to be v center of mass over r. I'm using capitals all of a sudden. And that's squared. So the r squareds cancel. It looks like all my m's cancel. And what do I have? I've got a gh is equal to 1/2 v squared plus 1/3 v squared. So I can solve for v center of mass now. What is that? 5/6, 6/5 GH equals v center of mass. Okay, so that was just a quick example, something rolling, how you'd use energy conservation, how you'd break up that rolling, that kind of complicated rolling motion into translation plus pure rotation, and we just account for the two different kinetic energies the way we did here on the right side.